In this lecture, we will see how to select a PIC controller and how to design a minimum system. The minimum system is the one where you don't need to have any external peripherals, just a single controller which is interfaced to input-output devices. So as far as the PIC family is concerned, so PIC controller we will get either 8-bit or 16-bit, or the latest advanced version is even 32-bit. But before that, let us see what are the types of architectures available. We get CPUs like CISC controllers, which is a complex instruction set computer, which is used in like 8085, 8086, 8051, where we always seen that the number of instructions are more than 100, and many addressing modes. They usually take more than one clock cycle to execute a instruction. Like say for example in Motorola SC05 controller, to load the accumulator by 55, it's a 2-byte instruction. So this instruction will take 2 cycles for execution. PIC is basically a Harvard architecture, which is known as a RISC controller, reduced instruction set computer. It is also used in other architectures like Spark, Alpha, Atmel, and so on. So as the name says, the number of instructions are less than 50, and the addressing modes are also very few. RISC architecture usually takes for per instruction one clock cycle. Like say move LW55 will take this one word 16-bit instruction in one cycle, it will be executed. So PIC is not one type. PIC is a series of CPUs are there. 12-bit core, that is the instruction size is 12-bit. So 12-bit instruction is a 12C50, 16C5 is the family which has 33 instructions. Then 14-bit core, that means 14-bit instruction size, is supported in 12C67 and 16C series, which has 35 instructions. Then the size of the instructions is 16-bit in 17C4 and 17C7 architecture, where 58 instructions are there. We are talking about a PIC controller, which is 18C series, which is enhanced 16-bit core with 77 instructions. So we will be talking about majorly 18 series controller, because that is how the board is designed, which is one of the latest series of the controllers. So if you look at the packages of the PIC controller, the package is available in 8-pin DIP or SOIC, and as you can see, the 12C50 and 12C67 are 8-pin ICs. Similarly, 16-pin is 16C series, 28-pin DIP, 40-pin DIP. We are talking about 18F series, which we get somewhere around 44-pin to 68-pin PLCC or TQFP packages. So the higher version has more number of input output lines, so that is why the number of pins are more. And now they are more or less coming, DIP is discontinued now in this 16-bit series, 16-bit instruction size. They are all SMD packages. The operating speed of the controller, so First of all, it is, if you look at the PIC clock source, PIC is not one clock source. PIC can use crystals, clock oscillators, or even internal RC circuit. They have built in inside the IC itself up to 4 MHz RC clock source. Of course, they are not very accurate, but the advantage is you don't need any external components. So internal oscillator is good enough to operate the device. The PIC family can up to right from 4 MHz to around 18F series up to operate 40 MHz to 48 MHz is the speed of these controllers. The program memory, as being a Harvard architecture, the program memory is different and data memory is different. The program memory for PIC controllers, as can you see, based on the size of the instruction, they are available from 512 bytes to 16 kilo words or 32 kilobytes in case of a 18F4550, which we are going to use in this board design. So PIC can store the program in two different types of memories, either in EPROM, which is erasable programmable read-only memory, which has a quartz window to erase by using ultraviolet light. And while programming, you require a higher voltage up to 13 volts to program this chip. So the C family is a EPROM version, which is obsolete now. The other family for program memory is called flash memory, which is currently used, which is rewritable even by chip itself. So you don't need any external programmer. You don't need any higher voltages. It is much faster for project development, and you can erase it and program it in millions of times. So wherever you see the PIC family F series is there, that is the flash program memory, where you can have millions of write cycles. Then about the data memory, as we have discussed, program memory, like in case of 18F series, the size of the instruction may be up to 16 bit, but data memory, if you see, we are always talking about the file registers of the RAM or the data memory are 8 bits. So the 12C508, for example, has 25 bytes, but however, if you are talking about 18F4550, up to 2 kilobytes of RAM space is there. So RAM is, as you can see, is a limited RAM. So based on your application, you have to carefully choose the controller because limited space of RAM is there. There are some special function registers are there in PIC controller apart from your RAM space. So these are meant for peripherals. These are also storage element, but we called as a special function registers. Like say for example, there is a status register which is meant for selection of the banks or indicate the status of your arithmetic and logic operations by zero flag, borrow flag, carry flag. Similarly, there is a register for interrupt control, enable, disable register. TRIS register meant for input output ports, which will decide the direction and the status of the pins. Then there is a TX register meant for transmitting the data and so on. So these are registers, but special function registers for controlling the peripherals and their behavior. The peripherals in PIC controller are different based on the different different PIC controllers you have selected. But most of them have input output ports. Almost all the, how small you select a PIC controller, they have the digitally programmable input output lines, Some advanced controllers have inbuilt A to D converters. Up to 12-bit is the resolution. 50 kilo samples is the sampling time. And serial communication, UART, SPI, I2C, and CAN bus protocols are inbuilt. Pulse width modulation up to 10-bit resolution. Timers and counters up to 16-bit resolution, including LCD drivers, watchdog timers. Some of the peripherals are there on chip in the PIC controllers. So as I said, all PICs have digital input output lines, what we called as a ports. Depends on the size of the IC. For example, a 8-pin PIC controller has 4 digital IO lines, and a 68-pin PIC controller has up to 66 digital input output lines. There are two control registers which will decide, one, the direction of the pin, second, the data, whether the data is high or low state. The driving capability of the pins are up to 25 milliamperes of sourcing and sinking current, which is good enough to directly drive the LEDs. So you don't need any external drivers for that. But one should know that though we are saying ports, these ports are having multiple functions, not only general purpose input output. They also have special functions like serial ports, timers, interrupts, ADC, DAC, and so on. The peripherals like A to D converters, they're available up to resolution of 14-bit and 16-bit cores. But they are available on 14-bit and 16-bit cores, these A to D converters. Sampling rate is available even up to 54 kilohertz. They are resolution is up to 10-bit or 12 bits with a accuracy of plus or minus 1 LSP. They are also available in sleep mode and so on to save the power. And they are in multiplexed form so that you can have multiple channels at the input of the controller. Similarly, the other peripherals are like UART and USART, synchronous asynchronous receiver transmitter, is available on 14-bit and 16-bit cores. The baud rate is up to 115 kilobits per second. Size of the data can be 8-bit or 9-bit with parity start and stop bits. But as we know, when the controller is operating on 5 volts or 3.3 volts, you need to have a level shifter like MAX232 IC for interfacing to the personal computer for data transfer operations. In the communication, there is also a synchronous communication. The previous one is the asynchronous communication. In synchronous communication, you always has a clock source. Like in SPI, serial peripheral interface, you have signals like master out, slave in, or slave in, master out, and there is a common clock will be there. Similarly, in I2C bus, though it is a two-wire communication, you have data as well as the clock. So which is generally meant for interfacing devices like EPROMs, ADCs, DACs, and so on. The timer counters are there in almost all controllers. They're 8-bit or 16-bit resolution, and with a prescaler, so that the clock which is applied to these timer counters can be programmable. So the most important event in the timers is once the timer overflows, they will generate an interrupt. The external pins, we can use the microcontroller as a clock source so that the timers can operate even by using the external pins. But remember, some of the peripherals make use of these timers. When we are using the timer counters, they also have some other features like capture, compare, and PWM, CCP. So, like in case of a pulse width modulation, you can have a resolution of 10 bit or 8 bit in the microcontrollers, and you can have a frequencies up to 19.5 kilohertz of 10 bit resolution or 40 kilohertz of 8 bit resolution, and so on. So pulse width modulation is inbuilt majorly, which is used in power electronic applications. Similarly, capture and compare, which is meant for measurement of the width of the pulses on the external pins. So you can apply a pulse width measurement signal on a pin of the microcontroller to measure the width, or the compare is where you can generate a signal based on the timer counter value. So whenever the counter reaches to the compare value, then the microcontroller pin can change its state from high state to low state, or low state to high state, or complement of the previous state, which is a programmable. So capture compare PWM, which is the advanced features of any timer counter. The other options or features of the peripherals are like sleep mode, so that which will shut down until the interrupt occurs and will wake up on the interrupt, or generation of a interrupt on the change of state on a digital pin, or watchdog timer, which is meant for deadlocks, to overcome the deadlocks, or brownout detection, so that whenever the voltage level falls below a specific value, it will reset the controller, or inbuilt LCD drivers, CAN controllers, and so on. So these are some other miscellaneous functions of the peripherals. You can also have a virtual peripherals. So virtual peripherals are, by using software, you can implement these serial communication, timers, and so on. But however, whenever you emulate any peripheral, it occupies a lot of space in your controller. So it is, when you want to implement a multitasking environment, so it is always better to use the peripheral, so that the tasks are happening simultaneously, though you have a sequential execution. Now let us see how this board of 18F4550 is designed. So why we have selected 18F4550? So if you refer the data sheet of PIC 18F4550, which is, as you can see, 4 ICs are there in this family, which supports the same thing. So most important feature of this 18F series is it has a inbuilt USB. So since the controller has a inbuilt USB bus is there inbuilt. So for programming this chip, we don't need to have any external programmer like PIC3, which is a programmer for the microchip controllers by using externally. So that program is not required if you have a USB inbuilt. So we will see how to program this controller through USB port. So when you choose this controller, first of all we need to see what is the internal resources available, because we are looking for single chip solutions. So being a single chip solution, we are worried about the resources like memory, like RAM, flash, timers, A to D converters, and so on. So let us see. For example, we have selected the PIC 18F4550. That means it has 32 kilobytes of flash is there, and 2 kilobytes of RAM is there, and 256 bytes of EPROM. 35 input output lines are there. It has a inbuilt A to D converter of 13 channels. That means 13 analog signals you can give it, where the resolution is 10 bit. Capture compare PWM is there. in this controller. Then along with that other serial communications like SPI, I2C and USART, comparators, timers, they are there in this. So one 8-bit timer and three 16-bit timers are there in this controller. As you can see, the family of PIC controller, the packages are different. They are all almost either SOIC package or DIP package. Since we are using PIC 18F4550, as you can see, the package what we are using is TQFP package, which is a 44-pin package, surface mounted device. So the device features, as we have already discussed, that in PIC 18F4550 we can operate up to 48 megahertz this controller. You can choose the clock anywhere from DC to 48 megahertz. 32 kilobytes are there, or 16K words are there of program memory. Data memory is 2 kilobytes. Number of interrupt sources are 20. The port names we called as the IO ports we called as A, B, C, D, E. So total 5 ports are there. Number of timers are 4, one 8-bit and 3 16-bit. Capture, compare, PWM modes are available. Serial communication is there. USB is there. 10-bit ADC with 13 channels are there. Comparators are there. There are number of ways to reset your microcontroller, including watchdog timer, brownout, stack overflow, or there is a beauty, there is a reset instruction. So you can write a reset instruction to reset the microcontroller itself internally through software. 75 instructions are there in PIC 18F4550 with 83 extended instruction set. We are using the IC package 44-pin TQFP package. So whenever we design the board, you should know first of all how to interface the oscillator, because without clock no controller will work, because these are all digitally synchronous devices. So the clock source, as you can see, there are 12 ways of choosing the clock source, which is programmable configurations. The clock is a crystal or a resonator, or the crystal resonator with PLL is possible, or high speed crystal resonator or high speed crystal resonator with PLL. So what you can notice is with PLL, without PLL we are talking. So that means one should know what is phase lock loop operation in a microcontroller. Then there is another external clock which is having divide by 4 option, or external clock input on RA6 pin of the controller, or external clock with PLL enabled. You need to look at that option, or external clock with PLL enabled IO on RA6. Then internal oscillator, as you can use as a without using any external clock. You can also use a internal oscillator in this microcontroller. And then for high speed oscillator used as a USB clock source, or and so on. So you have options of choosing along with the internal oscillator for the other, for USB, what is the clock source you want to use. So this is how one can choose whether internal oscillator or external crystal resonators or high speed crystals with PLL, without PLL. So these are various sources of the oscillator configuration. So PIC has option of choosing your own clock source. If you see the internal design of the PIC controller, there is a oscillator input, what we call as a primary oscillator. So by programming you can send this into a sleep mode, or you can activate this one, which will go to a PLL, prescaler. So as you can see, you have a choice of choosing the whatever is the crystal oscillator you have connected, that can be divided by 1 up to divided by 12. So you can choose what is the dividing factor for the primary oscillator, that which is oscillator 1 and 2, where you have to connect a external clock source. So PLL division factor, you choose the with the help of a multiplexer what is the clock source. So then this clock internally it uses PLL to make it up to 96 megahertz, which act as a clock source to your USB peripherals after dividing by 2. So that means around 48 megahertz is the clock source for a USB controller. Or this can be high speed PLL can be used as a clock source to the CPU by again choosing a CPU division factor. So this is PLL division factor. Here this is the CPU division factor. So 96 megahertz divided by this dividing factor can also act as a CPU clock source by using FOSC0 to FOSC3 control bits of a register. Or you can also see that external crystal will directly choose the CPU dividing factor with a oscillator post prescaler, and you can choose whether what is the type of clock source you want. So with the dividing factor, again it also acts as a primary clock source to your CPU or a peripheral. As you can see, when you are giving a clock source to CPU, you can disable by IDLEN bit so that the CPU enter into a sleep mode. So this is how you have a choice of choosing the from the primary oscillator whatever is the crystal you have connected. So what is the final clock to the CPU and to the peripherals and the USB peripherals by using prescaler values, which are nothing but dividing the clock source. Then about the secondary oscillator. So there is another clock source. You can connect it on T1 oscillator I and oscillator O, secondary oscillator. Again, it can be enable or disable by using a control bit. So this can be your clock source to your peripherals or CPU or other optional modules. And you also has, as you can see, another clock source, what is called internal oscillator block, which is programmable by using oscillator con bits of 4 and 6. So this internal oscillator, which is a RC oscillator, has a source up to 8 megahertz. It can generate a clock source. So again, now as you can see, this you can have a choice of choosing the prescaler value, so that now this will act as a internal oscillator to the peripherals or to the CPU. So one can choose what is the operating speed by using this internal oscillator. But however, as we can know, this is maximum we can go up to 8 megahertz, somewhere around 31 kilohertz to 8 megahertz is the operating speed. And this is not stable because this works based on the RC component. So as the temperature changes, there is a possibility of drift in the oscillation. So basically we have three sources. One is internal oscillator, secondary oscillator and primary oscillator. And then again you have choice of choosing with PLL, without PLL of these oscillators and the prescaler values, so that the user has a choice of choosing the operating speed of the microcontroller. So before writing or before designing the system, you should worry about the clock source, because all the internal calculations of the your software is based on the clock source. So we are using the high speed crystal HS oscillator in our board design. So this high speed crystal we will use 20 megahertz is the crystal. So 20 megahertz we will interface to our microcontroller, that is 18F4550, where as recommended, when you are using 20 megahertz, at least 15 picofarad is the biasing capacitors you have to use. So whenever you are designing any board, so one has to refer the data sheet which will tell the specifications of the uh, crystal and the biasing values which one has to interface. If you are using a ceramic resonators, then as you can see the biasing values are different. So that has to be taken care while designing the board. So the minimum system design is, as you can see, the IC3, which is 18F4550 44-pin TQFP package, is interfaced with first about, since as we know minimum system means without using any programmer how to load the program. So minimum system design means, so this controller how to program it. As you can see, there is a USB is there, which is the very next to the LCD connector. So this USB interface is meant for giving the power to the board and also to program the controller through USB. Since this PIC has inbuilt USB controller, so by loading the bootloader into this controller, we have made the board which is USB compatible for programming this chip. So the power supply to this board as well as the programming this board, this controller, is done by this connector, that is USB. So the in the minimum system, one is about the power supply, second is about the crystal. As you can see, you can connect up to this crystal can be 20 megahertz crystal, which is by using two biasing capacitors or 15 picofarad is interfaced to this controller. So the microcontroller, the crystal, high speed crystal, is about 20 megahertz is the operating speed. Then about the optional things. One is, since we want to make it USB enable, we have provided this programming connector which we will use the external programmer like PIC3 to program the bootloader, so that later on you don't need to have any programmer. Through USB you can program your application program. So first time we load the bootloader by using this connector. As you can see, this is the pin number 1 for programming the boot program. The Apart from the minimum system, we have provided few options, like there are ports are there on this board on a 5 by 2 D connector, and then there are two switches. One is called boot switch, so that whenever you want to make it enable for programming through USB, so you have to use this boot switch. And there is this S1 is nothing but a reset switch. And then the few LEDs are provided. One is to indicate the power, and other two LEDs are connected to the microcontroller. And the serial communication, UART, is since is inbuilt. If you want to connect to the computer's serial port, we have used a IC which will convert from uh, RS232, that is the signals, into the TTL and so on. So that means this USB is, you can connect it to the computer's USB, so that for a data transfer by using UART you can implement. So we'll discuss about the design part of this. And all other ports like ADC channels, interrupt, and another ADC channel, they are provided on the pins. There is a 16 by 2 LCD connector is provided for interfacing the LCD. And if you want to give the power supply, right now we are using giving the power to USB, or without that also you can give the provide the power by using this DC connector, so that if you have a DC adapter of 9 volts, you can give the DC supply here, so that this regulator 7805 will give the power to the board. So now the board is operating on 5 volts DC supply by using USB, or you can use a 9 volts DC adapter by connecting here. So this is what is the minimum system. Let us see the circuit diagram how it is designed. So just to begin with, the minimum system design means, as you can see, 18F4550, which is a 44 pin TQFP package. So being a minimum system, first of all one need to interface the crystal which is there on pin number 30 and 31. A 20 megahertz crystal is connected here with a biasing capacitors of 15 picofarad, and in parallel to the crystal 1 mega ohms resistor is connected. So this is the minimum system to operate this device, which act as a clock source, though it has an internal clock, but we want to use a high speed crystal HT. Then about the power supply, as you can see, pin number 28 is 5 volts power supply, and pin 29 is the ground signal. Then the other clock sources for A to D converter, the reference voltage is on pin number 22 is connected here. And then there is a pin number 7 for digital volts is 5 volts, pin number 6 is ground. So that is what is the minimum system is called. So we have given power supply, we have connected the crystal and the required VCC and ground wherever it is specified. That completes the minimum system. But since we want to burn the bootloader, or we want to load a application program, then there is a connector, as you can see, this 6 pin connector, PIC ICS PPTH connector. This is meant for programming the flash memory of the controller by using a PIC-3 external programmer from the PIC microchip company. So this connector interface requires, as you can see, the first pin is VPP, which is where we have connected the power supply of this we have connected this VPP pin to the VPP pin of the microcontroller, which is nothing but pin number 18, master clear pin. And the second pin is power supply pin, which is a 5 volts you need to connect. Then third pin is ground. After that, the programming signals like this fourth pin, which is connected to this PGD pin. Then the fifth pin is PGC pin, which is pin number 16, and sixth pin is PGM signal with a series resistor of 470 ohms. So this connector with these 6 signals is good enough to program the flash memory of the PIC by using PIC programmer. However, since we do not want to use PIC programmer for rest of the applications, we have used a USB interface, so that through USB also you can load your application program, provided once the bootloader is inbuilt inside the controller. So USB interface to this PIC controller is done by pin number 42 and 43, as you can see, D plus and D minus. So D plus should be connected to pin number 3 of USB, D minus should be connected to pin number 2, and as we know, USB provides the power supply of 5 volts is 1 and 4th is ground. So the moment if you connect the USB to the computer, so this board will get the power on pin number 1 and 4, and the USB without any external components, directly the USB connector you can connect it to the PIC. So this USB is good enough to give the power to the board. Also programming is done with the help of a bootloader. Otherwise, we also provided a separate power supply, so that in case when computer is not there, still if you want to operate your board, then there is a power jack is there, and there is a regulator IC 7805. So if you give a 9 volts DC supply, it will regulate to 5 volts. So this entire board also get the 5 volts from this regulator and a DC adapter. To indicate the power, we have provided one LED which is connected to 5 volts, other end is connected to ground by using current limiting resistor of 2.2 kilo ohms. So LED 1 is to indicate the power the moment you give the power, either through USB or through DC adapter. Then about the other optional, these are all rest of them are optional things. Like we have provided two LEDs on the board where we have connected a 330 ohms current limiting resistor to this LED. So the microcontroller's ports, that is RA4 and RA5. So port A, RA4, that is pin number 23 and 24. So A4, A5 we have connected to two LEDs so that you can write a program. We will see how to make the port bits as output ports and uh, write the data either high state or low state. There is a two switches are there for this. So one switch is, as you can see, connected to RB4, what is called as a boot. So this is where RB4, that is CSSSPP, this pin, this signal is meant for to change the state from boot mode to the application mode and so on. So whenever we are programming, we will be using these two switches. One is connected on RB4, other is connected to, as we know, VPP, that is nothing but master clear. So master clear is nothing but reset pin of the microcontroller, which is a active low. So being a active low, as you can see, whenever you press this switch, this pin will be active low. Whenever you release this switch, this pin goes to active high. So whenever you want to reset the microcontroller, you have to press this S1 so that master clear will be active low. And to change the mode of operation from boot load to the application program, you have to press this boot switch. Again, as you can see, RB4, whenever you press this, then it will be active low, and whenever you release it, it will be active high. So these two switches are meant for one to reset, other to change the mode of operation. But later on you can also use RB4 just to give the data also once the program is in the application mode. The other interface for this microcontroller is LCD. LCD, as we know, is a 16 pin connector, which is a text LCD, 16 by 2 or 16 by 40, 16 by 20 type of LCDs we can interface, where it requires 3 control signals and 4 data lines for interfacing the LCD. So as we know, pin number 1 is ground, pin number 2 is 5 volts, pin number 3 is contrast adjustment. We are connected to ground by using 1 kilo ohms resistor. Now pin number 4 is control signals, RS, read oblique write bar, enable for a LCD. So these 3 control signals we have connected to microcontroller's port D, that is RD0, RD1 and RD2. So port D we have used for interfacing the LCD. Pin number 7 to pin number 10 we have not used because LCD we are interfacing in 4-bit mode, not 8-bit mode. That means whenever we write the data to the LCD, we send the data in upper nibble, not on lower nibble. So we require only 4 data lines. So same port we have used D4, D5, D6 and D7. So these 4 lines are meant for sending the data nibble by nibble. And again, we require 5 volts on pin number 15 and ground on 16 to make the LCD LED on. So we have a yellow LED, what is called backlit LED, to make it on. So 15 and 16 has to be connected. So contrast adjustment of the LCD is done by this 1 kilo ohms. So if you want to adjust the darkness of the LCD, change the value by increasing or decreasing, you will notice the darkness of the character will change. And this port, as far as port of the microcontroller is concerned, you can use any port, but you have to worry about the port is used for any other purpose. If you have any free port, use that port. In our case, we have used only port D because that port we are not using any other purpose. So in a port D, we require 4 plus 3, total 7 lines for interfacing the LCD in 4-bit form. Then all the ports we have brought it outside. As you can see here, there is a interrupt, we have brought it out. ADC we have connected on 3-pin connector. If you want to connect a keyboard, then we have provided the port C. Then if you want to connect the ADC, then all ADC channel we have provided on ADC connector. Then complete port D and port B we have brought it on the 5 by 2 box type connector. So this is, I mean, these are all optional things, optional connectors, so that if you want to interface any external like keyboards or any motors and all drivers, if you want to interface, you can interface to these port lines. So that is, in short, is the minimum system. But since this microcontroller also has a serial communication, that is RC6 and RC7, we know this RC6 and RC7 of this controller also act as a TXT, and RC7, that is this RXT. So serial communication UART is available on RC6 and RC7, which is a TTL signal. So if you want to connect any Bluetooth or Zigbee, directly you can connect it here. But if you want to connect to the computer serial port is a RS232 standard. That means these voltage levels you will have to bring it to the plus 12 and minus 12 volts. So for that you require a IC driver like MAX232. In the earlier designs like AVR controllers and ARM processors, we have used the MAX232 IC, which you can refer in the videos. But in this board, we have used, there is a driver IC called FT232 RL device, so that this serial communication also we can do it by using USB. So because the laptops doesn't have serial port, so through USB, if you want to implement the UART communication, then this IC will convert the RS232, that is TXT RXT signals, into USB form. So that is the advantage of this driver IC. So it is like a USB to UART converter. So this UART USB port, if you connect it to the computer's USB, then this is called virtual port. Virtual port means it is dynamically allocate the USB into the serial port. That we will see in the example program. This is a optional device, so that in case if your PCs doesn't have UART, through USB also you can implement the UART communication protocol, which is again a different IC which need to be connected. The placement of the components on the board, as you can see, the microcontroller is here, IC3. This is the pin number 1 of the IC. The programming is done by using this USB connector, which is in the middle of your PCB. This USB connector is meant for serial communication. So for programming we will be using, but if you want UART for data transfer, you can use this, which is a application later on you can implement. And the programming of the flash is done by this connector. So pin number 1 of this is here. Then the crystal, 20 megahertz crystal is connected here, and the boot switch is this, reset switch is this. Power LED is here, and LED 2, LED 3 is connected to the microcontroller port lines, that is LED 2 LED on RA4 and RA5. That is port A4 and A5 is LED 2 and LED 3 is here. All other IO lines are brought it outside. As you can see, port B is here, that is which is next to your reset switch, and next to your LCD is port D connector is available here. One should know pin number 1, where the pin number 1 is there, so that there won't be any reverse connections. And there is a power supply. If you want to use any external DC adapter, you can connect it here, and there is a regulator IC very next to that. And this FT IC 232 IC, which is meant for converting UART protocol into RS232 form. So whenever you want to interface UART, you can connect it to the USB, so that by installing the driver on your computer, USB will act as a UART communication protocol. So that is how the minimum system design. Now let's see how to write a program for this PIC 18F4550 by using microchip compiler and loading the program by using open source bootloader programming.